back everyone to the November session of the Journal Club. Speaking now is Alex Gonzalez Fuentes, who kindly accepted our invitation to present his work on dark energy reconstruction and the crossing of the phantom divide. So the stage is yours.
Okay, thank you very much for the introduction. I will present my work on dark energy reconstruction and crossing of the phantom divide, which is based on these two papers in collaboration with my supervisor, Adrià Gómez-Valent, and the first one just accepted for publication in JCAP. So I guess that at this stage, most of us are familiar with these results, but essentially combining data from CMB, supernovae, and baryon acoustic oscillations from DESI suggests that dark energy might be dynamical instead of a static cosmological constant term. In lambda CDM, dark energy is this constant lambda, and these two parameters, W0 and WA, should be -1 and 0. But as you can see, the posteriors deviate significantly from that point. In fact, it's excluded at 2.8, 4.2 sigma, which now has been reduced to 3.2 with the latest DES reanalysis. There has been a lot of discussion trying to understand these results. But first, let's recall what these parameters mean. Well, they come from a linear parameterization of the equation of state as a function of the scale factor of the universe, so the pressure over the energy density. And it was originally conceived as a tool to compress information from phase space, in the sense that it can capture and identify the thawing or freezing behavior of a large class of models for dark energy. But it is more useful also to capture more exotic behaviors. If we focus on whether particular values of W0 and WA predict a crossing of the phantom line, so the -1 value, then this W0 and WA plane gets divided into four regions: the standard, quintessence, and phantom, where the equation of state is above or -1 during the whole expansion, and two regions where this parameterization predicts a crossing of the -1 line. So the quintum A from quintessence to phantom, and the opposite where the quintum B where the posteriors happen to lie. And in the intersection of these four regions, we have the lambda CDM, because for a cosmological constant, the equation of state is fixed automatically to be -1. So from this, it's obvious that this parameterization is useful to detect deviations from lambda CDM, but it's not clear what else can we infer when that is the case. In particular, we should be concerned about whether it is the case that the properties that we extract from the data through the lens of the CPL are really attributable to the physical entity causing cosmic acceleration. An example that clearly illustrates this comes from this paper by Wolf, Garcia, Bartlett, and Ferreira, where this black line is the equation of state for a thawing scalar field, which is frozen to be -1 during most of the expansion and then goes to values above -1. But if one generates mock data and feed the observables with the CPL, one can infer spuriously that there is this crossing to the phantom region, so to values below -1, when in reality this does not happen. So another limitation with the CPL was pointed out by Neseri, Sakrami, and Starkman, where they claim that in some way this truncation is injecting a lot of information not present in the data, and they instead consider more terms. They go to second order, which they call the CPL plus, and to third order, the CPL plus plus, and show that the marginalized constraints in this W0 WA plane broaden as you add more freedom. But for example, they get values of W0, which in this parameterization would be the present value of the equation of state, compatible with -1, whereas with the CPL we get a bit of attention. So before jumping to our method, I want to highlight that the limitations of the CPL and other parametric methods, it is not straightforward that they are overcome by using non-parametric methods like Gaussian processes, binning the data, some interpolation. Of course, we should use both and in a complementary way, But although these non-parametric methods are more model independent in the sense that they don't assume a functional form for which they fit the parameters, they also suffer from another problems. Like in particular, one must make a subjective choice on the hyperparameters like the number of pins, the number of nodes, which interpolator use. So all these limitations with the CPL and also non-parametric methods motivated us to address the problem with the weighted function regression method, which was developed in these two papers by Adrien Valen and Luca Mendola, where we let the data decide how we should account for different truncation orders that constitute a basis for our reconstruction. So if we conceive that every truncation order in, for example, the equation of state is a possible underlying model for dark energy, then we proceed in a Bayesian way and find that this means that we should assign to each of these models a weight that comes from bias factors. In practice, we approximate these bias factors by using Akaike information criteria, which not only simplifies it from the computational point of view, but also allows us to avoid discussing how prior weights impact the evidences. So from the definition of AIC for model J, where we have NJ additional parameters describing dark energy. So in the case of the CPL, it would be 2, WCDM 1. We see that this accounts for both the quality of the fit, but also penalizes the complexity as we add orders. So the picture that we expect for the weights is the following. When we start with a few parameters, then the data favors allowing more parameters to describe itself, because by allowing one more parameter, we get a significant improvement in the fit, and this outweighs the penalization term. But there's a point where the chi-square saturates and we don't get better by adding more freedom to our dark energy description. So this means that the very high order truncations are negligible and in practice can be neglected. So in a nutshell, what we have to do is to run an MCMC code for each truncation order, compute the weights, and from it reconstruct any quantity that can be built from the individual chains. Of course, using an expansion in powers of 1 minus a in the equation of state, which we call the W basis, is not completely free of assumptions. If we assume, of course, that the dark energy fluid is self-conserved, we can obtain the energy density, and we see that this does not allow for negative values. So in order to assess whether this is a possibility favored by the data, we also explore another basis, the rho basis, where we directly use a series expansion in the energy density. In this figure, we have the curves for the equation of state and normalized energy density for different combinations. Have a Planck 2018 likelihood with this supernovae, or Planck release 4 with Pantheon Plus, and this last dataset also with the rho basis. So from this, it is clear that once we go beyond the zeroth order, which in the equation of state basis would be the WCDM model, we get consistent shapes of the equation of state parameter, for example, in the sense that it doesn't deviate much. So this is also translated into the parameters. Here I have the results for the cosmological parameters for the individual models, and we see that they remain rather stable as we keep adding terms in our description of dark energy. In the last row, we have the weights for each model in this with this data set, and in particular, we see that the H0 value is on the low region. So this just reflects the fact that dynamical dark energy is not able to address the Hubble tension on its own. These figures represent the reconstructed shapes now using the weighted distribution for the our reconstruction. So we have the equation of state parameter, the energy density, and also we reconstruct the Hubble rate and deceleration parameter and jerk. Where in gray dashed lines, we have the lambda CDM values. For example, focusing on the equation of state parameter, we see that there is indeed this transition from values below -1 to above of it at redshift 0.4, 0.5, which means that this is not a spurious artifact of using a linear parameterization like the CPL. And this transition from phantom region to quintessence is translated into a peak in the energy density. But notice that also very interesting, we get values of the present equation of state which do not deviate significantly from -1, whereas with CPL only we got a bit of attention. And also this is imprinted into some deviations for the cosmographical functions, like the deceleration parameter. We get less deceleration in the past, and in the present less acceleration, just consistent with what DESI found. Here I show the comparison of this last dataset also with the two possible bases. And although there are mild differences, we see that the results are rather consistent. We have validated our method by by generating mock data for both lambda CDM and an extreme algebraic thawing model, where the equation of state is fixed at -1 until a recent abrupt transition. Even when including these higher orders in the expansion of the description of dark energy, we get consistent values of the equation of state of -1 in the case of lambda CDM. And in this very extreme model, we don't get any hint of a spurious phantom crossing. So this suggests that our method is not does not have any inherent bias that predicts spuriously phantom crossing or any other features of dark energy. These are the results for the reconstructed parameters, which also remain rather stable by changing the dataset and the basis. Beyond the standard parameters, we also include the transition redshift from deceleration to acceleration, the crossing redshift of this phantom divide, and the effective number of extra parameters to describe dark energy, which is between 2 and 3. And with the raw basis, we can quantify the probability of having negative energy density, which is of 2%, so not significant at all. This, in fact, with this method also allowed us to quantify what is the evidence for a crossing of the phantom divide, which we find to be between 96 and 99.9%, also in accordance with quantifications that appeared shortly after ours. Of course, we will have to wait until more data to make any strong claim, but if this signal remains and is real, then it poses serious theoretical problems, because the most compelling models, like a single scalar field, minimally coupled, cannot cross this phantom divide. So the natural question is, can we build a model that accounts for such phenomenology? The first naive idea that one would have to explain a crossing for the equation of state below -1 to above of it would be to include two fluids with constant equation of state, but this will not work. And in fact, if we impose the required phenomenology from our reconstructions to find which values of W1 and W2 are required, we see that this represents two non-intersecting surfaces, so there is no solution. This is valid for also for negative energy densities, but if we focus on the positive case, it is easy to understand why. If we have a constant equation of state below -1, then this phantom component to dominate in the past, since this implies that its derivative would be positive for the energy density, then we will always have a phantom component dominating, and we cannot explain this thawing behavior lately. So what we tried to do in our second paper was to reproduce this this behavior with a standard and negative quintessence, where we have this action for two scalar fields with a potential, and also this constant alpha in front of the kinetic term that can be plus or minus 1. From this, we can derive the Klein-Gordon equation, the energy and pressure, and this constant alpha will determine whether the field is losing or gaining energy with the expansion. So for the standard quintessence component, we fix this value to be plus 1, which is the standard, and we take a potential to be a constant and a standard mass term. So this is just describing a field that is throwing down its potential and losing energy. But with negative quintessence, this alpha is minus 1, so the field is gaining energy with the expansion, but we also take the potential to be this negative mass term. So since this is the inverted picture, then this field is gaining energy with the expansion, but it will climb the potential until it reaches the top. So this implies that negative quintessence has negative energy density and positive pressure, which are decreasing in absolute value as the field is reaching the top. In this diagram for rho and p with multiple components, we see that while phantom has the equation of state below minus 1 with positive energy and negative pressure, this negative quintessence component is on the opposite wedge as standard quintessence. So we have swapped the signs of the energy and pressure, but the equation of state is still above minus 1, like in the standard quintessence. These are the results of a fit to CMB, BAO, and supernovae data, where more yellow curves show a greater reduction of the chi-square as compared with lambda CDM, and in black we have the with the best fit. So we see that although neither of the components, standard or negative quintessence, individually show a crossing of the phantom line, it is the effective equation of state that reproduces this behavior of crossing from values below minus 1 to above of it, which translates into a peak in the energy density. In the last column, we show the profile distribution for the two masses of the scalar fields. And we see that there is a wide region of the parameter space that can yield low values of the chi-square. So this model is significantly affected by volume effects. These are the results for the comparison with the same data with lambda CDM, CPL, and standard and negative quintessence. And we see that this model is able to yield values of a minimum chi-square comparable to the ones found with CPL. Although it is true that at the level of information criteria, CPL is still favored because it has only 2 parameters, whereas with standard and negative quintessence, we have 4, the 2 masses and 2 initial values of the scalar field. However, we should remind that CPL is a parameterization while this model comes from an action that we can write down. So just to summarize, the weighted function regression method has allowed a model-agnostic reconstruction of cosmological quantities, which enable us to distinguish which features are really preferred by the data and not spurious artifacts of a specific parameterization. We have found consistent hints of dynamical dark energy consistent with DESI papers. And we have shown that this remains also when including higher orders in the expansion of the equation of state and the energy density. We find that data suggests a transition so a crossing of the phantom divide at redshift about 0.4, which we can quantify to be between 96 and 99.9%. And in the last part of my talk, I have explained that this does not necessarily require a real crossing of the phantom line, but can be mimicked by a combination of standard and negative quintessence. Thank you very much. I will take any questions.
Thank you, Alex. So much.